Welcome back to part 2 of thicker layers, where we look at the third possibility, where we apply material from the outside. This is going to be long again, so let us start with titanium nitride. Titanium nitride we could make on the surface of nitrogen. Let's say that again. Titanium nitride we could make on the surface of titanium by nitriding. In which case we would have a similar process to what we had on steel last time. That works fairly well. It also works on aluminium to form an aluminium nitride layer, which we will also consider here, because the other way to apply titanium nitride is to take it all from the gas phase, and then we're adding the material from the outside. So this is our process. We've got a surface of something, and we want to deposit titanium nitride, maybe titanium oxynitride, tungsten carbide, aluminium nitride, aluminium oxynitride, something like that on the surface, and it will be very hard. That will be our abrasive, cutting, or scratch resistant layer. So now the question is, how are we going to get this into a state where we can shoot it at our surface? And what properties does it need to have when it gets there? It turns out that they're not very soluble in very much at all, and it's quite difficult to get a stable solution of the things together and not have it react with oxygen from water or from the air or something. And so mostly we're going to have to work in a vacuum and the vapor phase instead. So now we're going to think of a way of doing that. So let's use titanium nitride. If we take a piece of titanium nitride, we could sputter it. So we can put our magnetron on here. That would be a magnet to direct the plasma, and that will generate some ions. Let's use argon ions because they are heavy and not very reactive, so we'll shoot them into our titanium nitride, and that will shoot off little clusters which will then go and hit our surface. But there's a problem with this. The problem with this is that the titanium is fine because it's going to go in a straight line and stick where it gets to, and if it goes anywhere else it will be lost. The nitride, on the other hand, is possibly going to connect to another nitride and form nitrogen, and maybe get pumped away into the puppets of gas. The problem with that is that our stoichiometry of our film, that started out perfect, is not going to be the same when it gets to here, because some of one or the other component will be lost on the way, typically the nitrogen. A way to avoid that is to add nitrogen here. So we're going to add some nitrogen, and maybe to separate the titanium and the nitrogen completely. So first of all we'll think of this. We're going to deposit a layer, and that would be fine. Let us consider what would happen if we divided the two processes completely. So now we can think of separating the process into a nitrogen launcher and a titanium launcher. Our titanium launcher could start off simply as a piece of titanium we heat up, and then it starts to evaporate. The simplest form of that would be a wire that we pass some current through, and it evaporates. It's not a very efficient way of doing it, because as we get close to the point where it will evaporate, it tends to melt, and so we will have a problem. But let's leave it like that to start with, because obviously I would have to rotate it 90 degrees to have a little dish so I can keep the liquid from falling on to the floor. Obviously that would be extremely messy and a massive problem in a design like this, so we wouldn't want to do it this way. We would have the titanium one at the bottom and the nitrogen one at the top, but I've drawn it upside down. If we want to just apply nitrogen, which is what I wanted to do before, it would work, but it wouldn't work very well. Why wouldn't it work very well? The titanium atoms coming along would react with the nitrogen and form titanium nitride, and they would stick to the surface. but we might not get the film that we want to, and it might not stick very well. That's because we want the material reaching our surface to have a high enough energy that it bonds to it, and we want it to have compressive stress. The reason we want it to have compressive stress is that if we generate some compressive stress in our film, we can make a better crystal structure, and compressive stress is good against cracks. If we're generating a material that is brittle, if it is compressed together, if we generate a crack in it, if we scratch the surface to start a crack, if it's compressed together, that's good because it will keep the crack shut. So from normal materials properties, ideally we would have compressive stress in our film, and a little bit of tensile stress in our substrate, but our substrate is very much thicker, so it's not going to damage it unless we only cut one side, and then it might bend slightly. So to do that, we need to apply some more energy, which is what I drew before. So now our nitrogen is coming into a separate chamber somewhere over here, which we're going to use to launch it towards our surface. And just like before, it's hard to launch nitrogen molecules, so we're going to first of all make it into nitrogen atoms. And we'll do that using some electrodes. So let's have an AC power supply. We could use a DC power supply, but we're going to break the nitrogen to make nitrogen ions. And then we are going to have an electrode, deciding whether, no, let's not bother focusing it. So now we're going to have an electrode which is made of a grid. That is, what are we going to choose? We're going to choose positive ions. So we're going to have a negative high voltage. We have a negative high voltage supply to here compared to the ground, which is here. This is a low voltage AC supply, which is breaking the nitrogen, and this is a high voltage supply, which is launching it, and it is launched out of this plasma region generally towards the surface. And we can choose, using the length of this Garnet arrangement, how straight the ions are going to travel, and we can choose with the voltage how fast they're going. Although obviously if we have too much stuff in the chamber, they're going to hit something on the way, so we need to have a relatively good vacuum for this. Then we can hit the surface with a known amount of energy, which is, as with the last process of nitriding, a massive advantage for control. Then we can generate a film that we want, which is, in this case, a titanium nitride film. If we want to add oxygen to the film, we can add a little bit of oxygen to the chamber, or we can add a third source. The problem with having everything in one source is exactly as before. We are forced by physics to take what we get, and then we might not get what we put in. This is a slightly simpler setup, where we could take the titanium metal and sputter it instead. So we're shooting argon ions into the titanium, making argon atoms, maybe some titanium atoms, maybe some titanium ions too. And we allow them to travel through a nitrogen plasma, which we have in between. The ions generated, we can accelerate towards our substrate by either their self-charge, but that's not very efficient and not very easily controllable, or we can control the voltage from behind. So that would make it a little bit simpler setup, but it's not quite as obvious to look at, and it's not as controllable. The problem with generating compressive stress is that although it does protect our coating from breaking due to scratching, it can't sustain a very high thickness, because as we increase the thickness of our stressed film, we're increasing the force, and we're not changing the thickness of the interface or the strength of the interface. So we've got some kind of thickness and strength of interface there, and we squeeze it to the same length. So we either stretch our substrate or we squeeze our layer to the same length, and we just let go, and that will eventually cause failure. What kind of failure? we can think about. So if we've got tensile stress, if we make the surface bigger, if we make the surface smaller than the underlying thing, we can see that in many cases. So if we look at drying paint or a lake that has dried out, some mud, we will typically see, first of all, square cracks, and then they will modify themselves and become mostly hexagonal. So we'll end up with a hexagonal-ish pattern of stress cracks in the surface that go down, and if these hexagons are quite big, they will tend to peel up on the edges as well, because they will also start to shrink. In the case of compressive stress, we have exactly the same problem, that our interface is stressed from the interfacial stress. It's trying to bend away, and also the film will crack in some places. So then we will tend to get delamination in the same way, but with a slightly different shape, and we won't get these cracks with gaps in between. We'll tend to get bits flaking off. So we need to think of some way around that if we're going to generate a thicker film. One way around it is to not make a thicker film, so to just have a thin coating and to use that. That would be what we would see in things like consumer grade drill bits and cutting tools, cheap cutting tools, because then we've got a thin layer that's hard. It will work very well, but then it will wear off because it's not very thick, and then it will stop working. That's ideal for tools that are intended by the manufacturer to be disposed of and then you buy a new one. It's not if you want a premium tool, and so typically we will have a thicker coating or some kind of better way of doing it. One better way that's thicker is to introduce layers in between of a softer material that can remove some of the stress, because it can release the stress in between, and so we can add layers that contain less nitrogen or less oxygen, so that are more metallic. So we start off with the base layer, which is typically a metal, then we have titanium nitride, then we have a titanium layer, then titanium nitride again, and then we can make a thicker layer. If we want to make a cutting tool, then typically we would not do that. We would typically use titanium carbide inserts, where you can make a piece out of titanium carbide, an actual solid chunk of titanium carbide. Start again. Tungsten carbide inserts, so you have a piece of tungsten carbide, which is the cutting hard surface, and that is added and bonded to the base material. That's different to a coating, so we won't consider it here. The other possibility from bringing material onto my surface is powder coating. We can do that in a variety of ways. Thermal powder coating, we're going to call it, because normal powder coating is where you coat the sample, your surface, with the powder, and then you sinter it afterwards to melt the powder and generate some kind of solid, or react the powder in some way to generate some kind of polymer solid. But what we're interested in here is a very high melting point material. So now we can think of that to belong with the other techniques. So we're going to imagine some titanium nitride particles that we want to bond to something. We're going to make some kind of abrasive disc or something. We want to bond titanium nitride to the surface to make it very hard, and we need it to get there and bond to it. Obviously these are very hard particles, so if we shoot them into it, it's going to be like sand blasting, and they're going to work into the surface and just abrade this away. So that's not going to be any good. Even if this is made out of stainless steel or something, it's going to be drilled away in no time by the super hard titanium nitride particles. So that's not going to work. What we need them to do is to get there with enough energy that they melt on arrival. There are a variety of ways of doing that, so we either heat them up beforehand, or we can heat them up purely with the kinetic energy. It's not going to work with titanium nitride because they need to get up to a very high temperature indeed, but it would work with some materials. So if we imagine we've got some zinc metallic particles, we can conceive that it is possible to get them to go fast enough that when they whack into the surface that they will melt and at least combine with each other, or not, maybe not melt, they will at least cold weld with each other. In reality, it's possible to get them hot enough from hitting the surface and working that they will actually melt, and that is if we get them going very fast indeed. Obviously, they're typically supersonic when they get there, and they will be blown by a very fast type of gun. But let us do the whole thing using the titanium nitride as an example, so that we can do the process in general, and then all of the variants of it are simplifications. So this is our process. We want titanium nitride particles to form a titanium nitride layer of some kind on the surface of our substrate, and it will be not hard enough to take titanium nitride particles whacking into it, but it's heat resistant enough that it can take them when they're very hot. Then we have some kind of blowgun to accelerate them, and we need to think about what properties that should have. So first of all, it obviously needs to accelerate them to a very high speed, so we're going to need gas coming in the back to accelerate them, and obviously our particles, gas, and we need to get a lot of energy in there. It's usually very difficult to get gas at such an extremely high pressure, so we should probably heat it up, because that's a good way to get energy into a gas, and then it will fly out of the end. We also want that titanium nitride not to react with the atmosphere and turn into a titanium oxide on the way, so we should use nitrogen, at least some nitrogen. Nitrogen has several advantages which get round a new problem that we're going to have. The new problem is, because we're going very, very fast, we don't have very long to heat up our particles. They have to get to about 2000 degrees, and that's tricky, because remember, they're going supersonically, and so we don't have a lot of time. We've got to accelerate them from the base of the gun to the front of the gun to supersonic velocity, so to over 330 meters per second inside our gun, and they only have the time of dwell inside there to get hot, and so we've got a problem of the two things not agreeing with each other very well. It's hard to get the heat in while having the speed, and the other problem is obviously that when we get out to here, if it's hot, the gas is going to be quite rare. If we're at 2000 degrees, there aren't a lot of gas molecules in the bit that's containing our titanium nitride. So the probability of the gas hitting the surface of our particles up here in the front part of the barrel is very low. The probability of hitting it where the pressure is higher at the back is good, but the probability of gas molecules hitting the surface of our solid further up is low, because although the pressure is still atmospheric, the temperature is very high, and so then the density of gas molecules drops. Here our nitrogen comes in very handy. So typically you would have thought, looking at this, what we want is argon in our gas, and that is a terrible gas for this. If you know anything about launching things into space from guns, or high-speed guns, multi-stage guns to get very, very high-speed projectiles, you will know that one of the problems is that the speed of expansion of the gas is the speed of sound in the gas, and so if we have a gas that's too heavy, then the speed of sound is lower, and then we have a bit of a problem. We don't get the speed per atom, per molecule, atom if it's argon, and then we are limited in our maximum speed, so typically a cannon that fires a projectile into space, so imaginary space cannon, a science fiction or planned space cannon to fire a satellite into space, for example, would have hydrogen that's launched out by some kind of explosive, and the hydrogen pushes into the barrel because hydrogen is very light, and then it can push the projectile, the satellite, along the barrel of the gun, and you would have it fed in multiple stages to get up to the speed that you want, which would typically be several times the speed of sound. That's difficult with any other gas because it's too heavy. Nitrogen has not that property because it's not the lightest gas, but it does have a different advantage. Nitrogen has a triple bond, and so if we break the nitrogen into nitrogen atoms, maybe make them positive as well, it doesn't really matter. Let's make the other one negative then. So we've broken our nitrogen into two ions. Then the good thing about those two ions is they contain lots of energy from the triple bond that we've broken. And so rather than ballistically whacking into our particles like the argon would have to do, they can stick to the particle and dump their chemical energy in by combining to form new nitrogen or by just bonding to the surface. So if we've taken our titanium, we've lost a little bit of nitrogen, new nitrogen, one of these ones can bond to it, and that dumps a lot of energy in. The typical temperature for this is over 2000 degrees. If we take a piece of titanium and nitride it by just setting it on fire in nitrogen, it will burn and heat up on its own to over 2000 degrees. So that's good because we get all of that energy back out, and likewise we can get the energy of nitrogen recombination out if we don't have any open bonds left over. So we can get more heat out of nitrogen than we can out of most gases because of this triple bond. There are a few other molecules that will do. We could obviously use oxygen, but then we're going to convert our titanium nitride into titanium oxide almost instantly if we do that. Obviously nitrogen is not going to sustain combustion, so if we do this by lighting a fire, we can't. We're going to have a fire, so we're going to have oxygen and some fuel. If we don't use a fire, we can use a plasma instead, so we can use an electric fire, and then we can generate a plasma. We're going to make it short, so we've got our, let's just make it plus and minus. It obviously wouldn't be a DC plasma. We light a little plasma in the end. That causes the gas to expand explosively, and we would have to close the end in some way to stop it blowing out the back, and that will push our titanium nitride out of the front. The plasma has enough energy because we can put in as much energy as we like. The plasma has enough energy to heat up our titanium nitride and cause it to fly out and melt at the surface at least, and it's pretty hot on the way. That's good because it means that when it hits the surface it will spread out, it will interact with the material behind, and it also means that it has a good chance of getting through any protective layers on the material that we have. This is a complete family of techniques, so we can go from the simplest kind where you have a combustion chamber here, so it's effectively really a gun, and it fires out the particles onto the surface, and you could manipulate it with your hands to one that is plasma and runs in a vacuum. Depending on how much money you're going to spend, what kind of high-tech device you want to make. If this is a sanding pad, obviously you've got a maximum cost that you can put up with. If it's going to be a part of a space shuttle, then you can spend more money. The length of the barrel is obviously a concern because the longer the barrel, the more gas we need per shot, but the faster it can go, but then we need to have it further away. Then obviously lots of things become more difficult. If it's too short, then we waste a lot of the energy because it just puffs out of the front and stays in the gas. So there tends to be a lot of optimization with these processes, and it matters what powder we put in and what we want to have. Obviously, yes, if we're going to have a nitride, it would be good to have nitrogen in our chamber as the working gas. If we want to get up to really high temperatures, we're pretty much forced to have nitrogen and plasma as the working mixture. If we want a lower temperature, so if we want to, for example, generate a glass coating of silicon dioxide, we only need to get up to a few hundred degrees, 500–600 degrees, and then combustion is fine. We can do that with fire. We can easily get to the temperature required, and we can shoot little glass particles and generate a film. Because particles are coming along, the film is going to build up a lot quicker than if we were going to put it down atom by atom, and so we can generate relatively thick films. But one of the problems is that the splats, as they hit, cool relatively quickly, and so they can often generate quite porous coatings, which can be good. So the insulation for turbine blades is typically made this way. The insulation for turbine blades for aero engines, for example, is titanium dioxide, which is applied in this way, and the pancake splats, each particle goes on, crashes, flattens and solidifies, and as long as we're far enough away from the heat source, it stays as it is. The blade is typically an alloy, could also be pure titanium, and the problem there is we don't want to melt it. The melting point of titanium dioxide is way higher than the melting point of the metal, and we want to coat it. We need to coat it with an insulating layer, because the blades that are inside the combustion chamber are going to be exposed to extremely high temperatures, and they're cooled with an internal flow of air or water, depending on which ones they are, and they need an insulating layer to stop the surface from getting too hot. And the insulating layer is obviously better if it contains pores so that it doesn't conduct very well. So we want these particles to cool every time. That has several good effects. It means that it's porous, but it also means that we protect the surface from the heat of the actual process of deposition as well, because we're only putting one on at a time, which is effectively a macroscopic version of sputter coating. Last time I went on about this for a really long time. I don't think it's a good idea. So I advise you to go and have a look at Wikipedia, for example, which has reasonable explanations of what goes on in here. What I'm particularly interested in is the chemistry and why you choose the parameters that you do.